Hello everyone. Thank you for listening to my presentation. I'm Aditya Sundarrajan and I'm going to present our work on Midgress-aware traffic provisioning for content delivery. Content delivery networks or CDNs deliver the vast majority of content over the internet today. When users request content that is hosted in the CDN, the request is sent to the closest edge server in the network. These edge servers are deployed in data centers all around the world. When the requested content is present in the edge server, the content is sent back to the user immediately. This scenario is called a cache hit and is the most desirable scenario as the content is delivered with low latency. However, if the content is not available in the edge server, then we have a cache miss. In this case, the content is fetched from the origin server and sent back to the end user. This is not desirable because the request needs to traverse the high latency WAN link over the internet. The traffic between the edge servers and the end user is called the egress traffic. This is not a cost overhead for CDNs as it is paid by content providers. However, the cache miss traffic, also called the midgress traffic, is a cost overhead that CDNs would like to minimize. CDNs have multiple performance and cost objectives that they would like to optimize. Three important ones are the end user latency, which is the time between requesting a content and sending it back to the end user, the origin offload ratio, which measures the fraction of content delivered by the origin, and the bandwidth cost, which is the cost of delivering content due to cache misses. A fourth metric that ties all of them together is the cache hit rate. To see how they are connected, we can see that when the cache hit rate is high, the end user latency is low, the origin offload ratio is high, and the bandwidth cost is low, all of which are desirable scenarios. Hence, we focus on cache hits or conversely minimizing the midgress traffic in CDNs. To understand the challenges with minimizing midgress, let's look at the scale of the problem. Let's consider a set of servers in the network. Let's also consider a bunch of content providers that host content in the CDN and a set of end users who request these content. Minimizing midgress in large CDNs is challenging because they have content from hundreds of content providers, hosted in hundreds of thousands of servers, and requested by millions of users around the world. Working at this scale is also challenging because CDNs have to take into account the constant change in traffic characteristics to minimize midgress. CDNs have two important systems that work together to achieve high hit rates. They are the cache management system and the traffic provisioning system. When users request content, the requests are classified into traffic classes. A traffic class is a collection of domains from a single content provider that have content with similar caching characteristics and performance requirements. Splitting into traffic classes helps CDNs manage the scale of traffic. So for example, here, CNN videos could be one traffic class, Facebook images could be one traffic class, Microsoft downloads could be another traffic class, and so on. The goal of the traffic provisioning system is to assign traffic classes to servers within the network by taking into account the available resources in these servers. The goal of the cache management system is to manage the content in cache so as to achieve high cache hit rates. These can be in the form of cache admission algorithms that decide what is admitted into the server and cache eviction algorithms that decide what is evicted from cache during eviction. The request routing algorithm is then responsible for routing user requests in real time to the servers that host the content. Past work has focused a lot on optimizing cache management algorithms and reducing midgress. In this work, we focus on the traffic provisioning system. Existing traffic provisioning systems don't explicitly reduce midgress. We propose traffic provisioning algorithms that explicitly reduce midgress and show that these approaches are complementary to any existing optimizations in the cache management system. To understand the challenges in optimizing traffic provisioning, let's consider this example here. We have these set of users requesting content for different traffic classes, and we have two servers. Now, One possible assignment of traffic classes is to assign all traffic for CNN and Facebook content and half of Microsoft downloads to server 1 and the remaining half of Microsoft downloads to server 2. Now this assignment would lead to some amount of midgress. However, as you can see, there are several possible assignments of these traffic classes to servers. In fact, the search space for the best traffic class assignment can grow rapidly as the number of traffic classes and the number of servers grow in large CDNs. And so to set our problem, given the different traffic classes, the goal of this work is to assign traffic classes to servers such that the midgress from the network is minimized. In this work, when multiple traffic classes are assigned to a server, we assume that these traffic classes share the cache space. In other words, there is only one eviction list. We model the traffic provisioning algorithms assuming stack-based algorithms like LRU are used. But in the paper, we show that these assumptions work well even when non-stack-based cache management algorithms are used. Now, to understand cache sharing, we use the notion of eviction age equality. Let's consider a cache with a single eviction list, where objects enter the cache at the head and are evicted from cache at the tail. The eviction age of an object is the time difference between the eviction and the last access for that object. And so when an object is accessed and it is placed at the head, and if it is never accessed again, the eviction age is the amount of time it takes for that object to go from the head to the tail. Given a large enough cache, we assume that all objects in a cache have the same eviction age, which implies that all traffic classes have the same eviction age, and this eviction age is also the eviction age of the cache itself. But how do we get the eviction age? For this, we use the notion of a footprint descriptor that was proposed in past work. A footprint descriptor of a request sequence of a traffic class is the joint probability distribution of the stack distance and the inter-arrival times of objects in the request trace. The stack distance of an object is the number of unique bytes that are requested between successive accesses of the same object, and the inter-arrival time is the time difference between successive accesses to the same object. And so how does this help with getting the eviction age? Once we have defined a footprint descriptor for a trace, we can compute several useful caching characteristics. Marginalizing along the stack distance axis, we can compute the hit rate as a function of the cache size. This is also popularly known as the hit rate curve, and we can also compute its converse, the miss rate curve. Marginalizing on the inter-arrival time axis, we can compute the hit rate as a function of eviction age. Finally, we can also compute the cache size as a function of eviction age and vice versa. Footprint descriptors can be computed efficiently and are constantly computed to account for changes in traffic variations. And so each time we compute the footprint descriptors, we can then compute these corresponding functions efficiently and quickly. Once we have the footprint descriptors, we can use the footprint descriptor calculus to determine the midgress traffic of a traffic mix. At a high level, the traffic mixing or addition operation involves adding two joint PDFs. Recall that these footprint descriptors FD1 and FD2 are joint PDFs. Mathematically, this translates to a convolution operation, which can be efficiently computed using algorithms like the fast Fourier transform. You can look at the corresponding paper for more information. Now, getting back to our problem setup. So how can we use footprint descriptors to optimize traffic provisioning? We use footprint descriptors in two places. First, we compute the footprint descriptor for each traffic class, and then we use that to obtain both the miss rate curve and the eviction age functions for those traffic classes. And second, we use the footprint descriptor calculus to compute the midgress of different traffic class assignments in a server. And then we can then add those midgress to give us the midgress of the entire network. Now, let's look at a pictorial representation of the optimization problem. Hopefully, this will clarify things even more. Let's say we have T traffic classes with loads lambda 1 through lambda T. Let's say we also have some N servers. Let xij be the fraction of traffic class j that is assigned to server I. Now these are just fractions, and so it's a number between 0 and 1. Then the goal of the traffic provisioning algorithm is to assign these traffic classes to servers such that the midgress is minimized and the cache storage and traffic capacity constraints are satisfied. Now, in the objective function, xij is a fractional value, and nj of cij is the misrate curve of traffic class j. And so that function is really computing the misrate of traffic class j when it occupies cache space Cij in server I. We assume that this curve is convex. The midgress in each server can then be computed using the footprint descriptor calculus that we just discussed. And so the total midgress of all of these servers then adds up to that objective. In the paper, we show that we can reduce this non-convex problem to a mixed integer linear program, but that mixed integer linear program is still an NP-hard problem to solve. And so while knowing the optimum is definitely valuable because it tells us what's the best we can achieve, we would like to have a faster heuristic that produces a result close to the optimum but also runs quickly. And so for this, we propose a heuristic that is a local search algorithm. The heuristic starts by making a random assignment of traffic classes to servers and computing the total midgress using the footprint descriptor calculus. In every step, we reassign traffic classes to servers until a point where the midgress doesn't reduce any further. The resulting assignment is the output of the local search algorithm. To see how these algorithms work, we consider a metro level scenario where we have a bunch of clusters with a number of servers in each cluster, and all of these clusters are located in the same metro area. The goal in the metro area scenario is to assign traffic classes to clusters such that the total midgress of the entire metro area is minimized. In the paper, we also consider a cluster level scenario where the goal is to assign traffic classes to servers such that the midgress traffic of each cluster is minimized. And so in the paper, we show how both the metro level traffic provisioning and the cluster level traffic provisioning problems can be modeled using the same optimization model. For this evaluation, we collected traces for 25 major traffic classes from a large metro area. These traffic classes were collected for different types of traffic, such as web, media, and download, and they were collected over a period of 16 days. Now, first we look at the cache miss rates for different algorithms. In this graph, we plot the cache miss rate of different traffic provisioning algorithms at different cache sizes. Opt is the solution of the optimization model. Local search is the heuristic that we just discussed in the previous slides. And baseline fit is a baseline midgress-unaware traffic provisioning algorithm that is similar to the traffic provisioning algorithms in use today. The baseline algorithm assigns traffic classes to servers using techniques such as consistent hashing without explicitly accounting for the impact on midgress due to these assignments. In this graph, smaller value is better. And as we can see, opt clearly outperforms the baseline, indicating that being midgress aware can complement any benefit that we achieve from cache management. Moreover, the performance of local search is very close to opt and runs at a fraction of the time, which makes it a great candidate for use in settings where traffic conditions change quickly and new traffic assignments need to be frequently computed. In the paper, we also discuss other scenarios where we show that midgress-aware traffic provisioning can be easily extended to accommodate other practical constraints, such as maintaining a minimum redundancy for each traffic class and enforcing a maximum limit on the cache miss rate for each traffic class. In the paper, we also show that the proposed traffic provisioning algorithms work well when used with cache management algorithms that are not stack-based. I encourage you to take a look at the paper if you're interested. Finally, throughout this talk, we have only worked with shared caches, where the servers have a single eviction list and the traffic classes share that cache space. We extend our traffic provisioning algorithms to work with partition caches as well. In the graph shown here, part indicates the partitioning counterpart of an algorithm. We can take away two things here. One, as expected, baseline fit part is better than baseline fit for a shared cache. This is because, given an assignment of traffic classes, it is known that a partition cache is always at least as good as a shared cache, if not better. And two, the opt for a partition cache is very close to the opt for a shared cache. This indicates that by being midgress-aware, traffic provisioning algorithms can work very well with shared caches. This motivates us to stick to shared caches in production settings. It should be noted that the optimization model with partition caches is still a mixed integer linear program, and so it's still an NP-hard problem to solve. Now, to conclude, in this work, we show that midgress-aware traffic provisioning can reduce the midgress by nearly 20% when compared to a midgress-unaware baseline. We also proposed a fast heuristic that performs almost as well as the optimum and is well suited for production settings. Finally, we showed how midgress-aware traffic provisioning can be extended to work with additional constraints such as minimum redundancy and maximum midgress, and with different cache management algorithms and with partition caches. I would like to thank my co-workers for their contributions and their help with this work. I also want to thank everyone for listening to my presentation. If you have any questions or clarifications, please feel free to contact me by email. Thank you.